Hello. This second video will begin with a model for C++ compilation. So let's go to that slide. Okay, so the C++ compilation process, the build process, is interesting. Several things happen. So when the build system processes a CPP file, or processes source code, it does that one CPP file at a time. Each of these translations of CPP files are independent of all the other CPP files. So no information is carried over in that translation process. So they're each done as individual entities. And that's actually, for very large systems, that's an advantage, because it means that the very large system is broken down into small pieces, each of which is translated. So we don't run into any issues with overflowing, compiler tables and so on. So we say that CPP file and all the files that it includes are a translation unit. What happens during this translation is the first thing that runs is a preprocessor. So it picks up a CPP file, and it includes, for each of the #include header files defined by that CPP file, it puts those header files in place at the site of the #include. And it does some other things to expand macros and handle other preprocessor definitions and so on. But the main function is to build a large intermediate source code file that has the CPP, the package CPP, and every one of its headers in one single intermediate source code file. Normally, we don't see that. We won't see it unless we ask the compiler to generate it for us. And it's, it's typically very big, because not only is it including other code that we may have written, but it's also including compiler library code, and IO streams and F streams and stuff like that. Okay, so we build this intermediate file, and then the compiler digests that and creates an object file. And if the options for the build process build a library, instead of building an object file, it builds a static library, for example, or it might build a dynamic link library. For the moment, let's assume it builds an object file. And so now it keeps stepping through all the CPP files, building object files or libraries or DLLs or whatever. And when we've come to the last of the CPP files, we have a collection of object files, and those all get bound together by the linker. The reason that's necessary is that when we compile a CPP file, any calls within that same translation unit get resolved immediately by the compiler. The compiler knows how all that code is laid out, and it just, when you make a call to some function, it just sets the address to jump to the right site of that function code, and away we go. But if you make a call outside of that translation unit, which we do all the time, one package makes a call into another package, the compiler can't resolve that. So it builds a table of unresolved references, and it's the linker that resolves all those references. Now, when the linker has all the OBJ files and or libraries, it's got all the things it needs to resolve those references. Basically what happens is, as it's compiling, it's building a link map, and all those references can be resolved within that link map. And so that results in an execution image. So all of the object files and any static library files that were built get resolved by the linker, and it builds an execution image. And that execution image can be loaded as soon as we ask it to run, it loads. Now, if it depends on any dynamic link libraries, those can't get resolved until load time. Because we don't want them, we don't want the linker to make them part of this execution image. Part of the idea of these dynamic link libraries is that we may never use them, so why put their source code into the execution image? And also that source code is shared, may be shared by many different execution images. So for lots of reasons, we don't want those dynamic link libraries bound into the execution image. So when we load, then the loader has to do that final resolution of unresolved references, just like the linker. It's often called a linking loader. And its job is just to bind any dynamic link libraries into the execution image, and then we get a running process running our program. So that's the build model for C++. And it works really well, has for years. It's, a lot of history behind the system. Yeah, the preprocessor has some quirks and people complain about that a lot, but basically it works fine. You might want to know that as of C++ 20, a new module-based system is coming that will downplay the use of header files, and that'll be interesting. There's only experimental libraries, module libraries in place now. I typically don't start working with a facility until it becomes an official part of the language, just because there's lots of stuff to look at and deal with, and you might as well wait until it's stable enough to invest some significant amount of time in. So anyway, this is the process we have as of C++ 17, and it's been the same process we've used for years, since almost the very beginning. It actually started with the C language and has continued through all the versions of C++, up through and including C++ 17. Okay, so one of the consequences of this build process is the definition first rule. The C++ compiler, the language was designed to support one-pass compilation. So what that means is that before we can create an instance of something, we need to know its size. The compiler can't lay out code for it until it knows how big it is, and the only way it knows how big it is to see the declaration for the class that we're creating an instance of, or whatever. So, so we have to see the definition first. We have to see the declaration first of a class before we can create an instance of that class. So you can create a pointer to an incomplete type. So maybe we've made a forward declaration like class A semicolon. So this just tells the compiler A is a name of a class, but it's not defined yet. So we can make a pointer to that incomplete type, but we can't use it to select or find the contents of that pointer, because the contents don't exist yet. So, but sometimes that's useful when we have dependencies. For example, when we build a graph class, a directed graph class, we might find that the vertices and edges are mutually dependent. A vertex is going to hold a bunch of edges, and each edge has to point to a specific vertex. And so they have to know about each other. That's a mutually dependent relationship. And so what that means is the only way this is going to work is that we create a forward declaration for one of those types, and then define the other type, and then below it, now we can define the type we can complete the incomplete type. So that's the way that works. So the definition first rule says instances of classes, structs, and enums can be created only after those entities are declared. And so, one mental model is, if you think of the CPP file as a big collection, an ocean of syntax, And the include files are like tributaries, rivers coming down, filling that ocean, the rivers of syntax. Then the entity declarations have to be upstream from the point of an entity creation. We have to have seen that declaration before we can create the instance. So here, upstream simply means a compiler scan order. Okay, so that's the C++ build process in a nutshell. Not too hard to understand, but you really need to know what those pieces are so you understand when things don't go well with the you get link errors or something like that. You really have to have a model of that build process to make sense out of the link errors. Okay, now for the second part of this video, I want to talk a little bit about program execution. So program model, every program has a main, which is the entry point for the program. That's where computation starts. Actually, there's some initialization code that runs when you load the process, but the real computation, the computation that you put in place, starts when you enter main. And in main may call a function, and that function may call another function, and that function may call another function. Each time a function is called, we create an allocation of stack memory, which is scratchpad memory. It's just temporary memory that we store the arguments of the function, any local data that's defined in the function, and so on. And we use them while the thread of execution is in that function. When the thread of execution leaves that function, that memory becomes invalid. The next time we enter another function or open another scope, we'll probably overwrite that memory. So it's becomes invalid as soon as we leave it. When we're implementing a function, let's say we're declaring some types, we have a lot of freedom about where we put those types. Unlike the managed languages, we can store an instance in static memory up in the same region where code is, and that static memory has a lifetime of the program. We can store an instance in stack memory. So if we're in a function and we just define a local variable in there, we're defining it in the stack allocation for that function. So we're allocating the stack memory. If we call new on an instance, then we're allocating it in the native heap, and the lifetime of that lives from the time we call new until we discard it with a call to delete. So these three memories have different lifetimes. Static memory has a lifetime of the program. Stack memory has a lifetime of the thread entering a scope until it leaves the scope. Scope may be a function, but it might be a lower level scope, like an if block, for example. Same thing happens there. And the lifetime of objects in heap memory start with a call to new and end with a call to delete. And we have some ways of interacting with the environment, cin, ifstream, cout, ofstream, carr, clog. These are all C++ streams, and we can use, probably don't, but we could use the C level libraries, standard in, standard out, standard error, and standard log. But usually we use streams. And by the way, cin and cout and carr and clog, you don't have to create those objects. They're global objects that are created when the library is loaded and initialized. So we just use them. Any place in the program we can use cout, for example. We don't have to create them. Okay. So here's program memory. So when the thread of execution enters a function, we allocate stack memory. Same thing happens for every scope. Program may place any of its entities, an instance of a user-defined class, into static memory, or heap memory. We've already described how that happens. And in the next model, we'll describe the consequences of that placement. So this streams interface is one way to interact with the environment. Another is that we accept arguments from the, if it's a console application, we'll accept arguments from the command line. And even if it's a graphical user interface, they have command lines, and all of the frameworks provide a way of getting access to that command line. So that's another way of interacting, at least acquiring inputs um, from the environment. And finally, our program can interact directly with a platform. This is native code, so we can make calls directly into the platform APIs. And exactly how we do that depends on uh, the platform we're on. For Windows, we pound include windows.h, and that includes lots of different header files, and most of the things we need we get that way. If we're programming for Linux platforms, typically we're loading each of the platform API libraries as we need them, and there's usually a cluster of them that get loaded, for the directory system and so on. Okay, so that ends the second video. So we've talked about the compilation model, and we've talked about an execution model. And in the next video, we'll continue that with a memory, begin that with a discussion of a memory model, and continue on from there. With that, let me thank you for your attention, and we may see you in a subsequent video, and if so, great. So with that, goodbye.